All right. Good morning, all. Please join me in welcoming Christian to Microsoft. So Christian's a lecturer at Bath, and previously he did a postdoc at, he's done postdocs at Max Planck Institute of Informatics Saarbrücken and INRIA Sofia Antipolis. And before then, even, he did his undergrad and PhD here in Cambridge with a number of us in the whole Lens Science team. So his research interests cover stuff from image processing, computer graphics, and computer vision, and he's going to be presenting some of his recent work on reconstructing faces and materials for 360-degree videos today.
Thank you very much for the introduction, Errol. Indeed, I had some difficulty finding a title covering all the things I want to talk about. I have a few things that I brought here with me today, so sort of choose your own adventure. I want to talk about the first 4 things. So these are all recent work this year. So the top paper is something we presented just a few weeks ago at IEEE VR in Reutlingen, Germany. And then there's 3 papers coming up at CVPR and SIGGRAPH. And then if you're really interested in any of the bottom topics and we have time at the end, then we can go over that. Or you just ask me afterwards. I'll be happy to talk about all of that. So let's get started then. So the first paper I want to talk about is called Parallax 360. So it's a novel image-based representation for 360-degree scenes with head motion parallax. So that is a new thing here. And essentially what we have with existing systems for stereo panoramas is that you get stereo disparity between the 2 images, but what you usually don't get is head motion parallax. When you move your head, you also want the scene to react to that. You want to be able to see behind objects as well. And that is currently not possible with stereoscopic panoramas, for example, with 360 3D movies on YouTube. But with this, our representation, you can see the bench, you can see behind the bench. As you move your head, it actually reacts to that. So it sort of started from the stereoscopic panoramas work. I've done a little bit of work on that on Mega Stereo back in 2013 with Disney Research in Zurich. But the main problem there is that everything's sort of baked together. You don't get any head motion parallax when you move your head. You just generate 2 views, one for the left, one for the right eye, and it's all sort of baked together. It doesn't react to your head movement. But what you really want, and sort of the scene at the top here, is head motion parallax. When you move your head, you want to be able to glance behind objects just a little bit. And to do that, one approach could be you want to reconstruct everything, 3D geometry, from some image data that you capture, or maybe from a depth sensor as well. That is definitely one approach you can do, but it's very challenging to do that with a very small capture radius. So state-of-the-art camera rigs for this sort of 360 video and image photography, these are sort of this size rigs, and from this sort of baseline, you don't usually get a very good reconstruction for 3D geometry, particularly when you go beyond a few meters away from you. So what we followed then is some sort of image-based representation. It's inspired by light fields, essentially. But we don't want to build these crazy camera rigs with hundreds of cameras, because that is very, very expensive. But we do want to capture essentially views from a lot of different positions so that we can synthesize new views correctly from intermediate viewpoints. And what we're doing there is we are sort of building an image-based representation that uses optical flow and motion data at several levels, essentially. So we're capturing a few different views on a sphere. In orange, you can see these are sort of the main views, and we're capturing the sphere regularly in a latitude-longitude grid. And for each of these points, we actually want to know a bit about the depth of the scene. So we have a curve-based representation that gives us sort of the disparity. Like if you move a little bit away from that viewpoint, from that keyframe, how would the scene deform? And then we want to be able to interpolate between pairs or even triplets of these keyframes. And what we actually capture to start with, we actually sample a lot of views. We capture all these keyframes. So these are regularly sampled, 5-degree steps on the sphere. And then around each, we capture a few relative frames. So 6 frames, a few centimeters away in a circular pattern, so that we see sort of a little bit of a baseline. What is the disparity or the motion there? And then we encode the motion relative of these relative frames relative to the keyframe and store that for each keyframe. And then we can throw away these relative frames. Because all we want to know is how does the scene deform when you go a little bit away from each keyframe. Okay. A moment. So we're actually capturing a lot of images that way, but we do not store all of them in the end. So we're capturing about 570 frames. These are the keyframes, and then around there, 6 times as many relative frames. Right? So there's a lot of frames, takes a lot of time, and we build a little robot to do that for us because it's very annoying to do manually. You don't want to do that. But it does take a long time to do that. So it takes about 2 hours to capture all the frames. And so you really want to do that only in a static scene where things are not moving. If you go outside, then even the shadows are moving a lot in 2 hours. So there's a few issues there. But this is a sort of a prototype. And you can then think about how you could build a camera rig that can capture that more easily. And Google's built one of these, and I have a picture later on of that. So it's definitely, there are ways of improving this design. But this gives us the most flexibility for our prototype when we can capture everything we're interested in with this simple setup. So I mentioned we build a curve-based representation. So we compute the optical flow between each of the relative frames and the keyframe, and then we encode them in a spline for extra robustness. So we don't actually have to encode all the optical flow fields that we get relative to each keyframe, but we sort of can compensate for some outliers there, make it a bit more robust and encode it that way. And sort of visualized as these 6 different colors for the 6 different directions of the relative frames, so we can then determine what is the motion, the disparity in a particular direction. And then we need to be able to, when we warp images together, adjust the motion direction based on this curve-based representation. The detail of that in the paper, I don't want to go over that here. But what we do is we use this disparity-based representation for each frame, and then combine it with a different motion, just a pairwise flow, so the flow field from image I to image J, and sort of have this 2 layers of motion fields that we use, right? So we have the motion that's sort of intrinsic for each individual view for each keyframe, and then we have some motion between each pair of adjacent keyframes in addition to that. And that will allow us to actually then synthesize a new target frame between each pair or a triplet of cameras. So what we're doing there is we're aligning all the views. So for example, we have 2 images, 2 views, image I and image 2, and we can use their pairwise flow to align them to the same reference, to the same one of them. So we usually use the first one, right? So we can align the images relative to each other using that these disparity-based ones. So these are not relative between pairs. They're just intrinsic for each image. So we use those. So essentially we use these disparity-based motion fields to warp them to intermediate positions. And then we use the pairwise flow to align them even better, to a flow-based blending, so that we can get rid of any misalignment artifacts, and we can avoid popping as we sort of transition between views, right? Because the selection of which pair of images might be best used for synthesizing a new view changes as you translate, for example, your head. And I have some videos that make this a bit clearer. And essentially, we don't want to compute these sort of alignment flow fields on the fly because they're quite expensive to compute. And if you want to look at this scene in a virtual reality headset, then ideally you want a real-time result, right? You want a really low latency response. And so what we're doing is we're using these pre-computed flows for stitching together, or computing this on the fly, and aligning all the different views together and blending them together smoothly. So let's have a look how this looks like in the previous technology in stereo panoramas. So you do see 2 different views for the left and the right eye. You can see behind the leg of the statue, for example, there you see different amounts of the background. But when you move the head, it doesn't actually change how much of the background do you see. And with our method, you do get both the stereo disparity, so 2 different views, stereo vision. You can see different amounts behind the leg, and also as you move the head, you can see that the leg actually occludes the background as you would expect it to happen. So you get the head motion parallax additionally. So that's very, so the key contribution or the key advantage of our approach is that you can get the head motion parallax as well. So it's more immersive, gives you a better depth perception of a scene. The previous one looks sort of a bit flat. You still get the stereo disparity, like I said, the stereo vision, but it doesn't react to a head movement actually. is also very visible in this particular carefully constructed scene. So here, as the person looks around, you can see there's a vase. You will see later that there's also a flower pot behind the vase. But with the stereo panoramas, you never see that because it's always occluded by the by the vase in front. So there's no head motion parallax. But with our approach, you see both the stereo disparities, all right, slightly different views, but you already see there's a flower behind the vase as well. As you move the head, you can see the flower pot emerging on the other side of the vase as well, as you would expect it to happen in real life as well. Right, so stereo panoramas, no flower pot. With our head motion parallax supporting representation, we actually can see behind the vase. Then I want to show you a comparison of this flow-based blending technique that I discussed earlier. So we compared it to different baselines. One baseline was to just pick the nearest keyframe. So this sort of would really switch around a lot. As you move your head, it would always select the next keyframe. And another simple thing one can do on top of that is to do alpha blending between each pair. So you always switch from one pair to the next, to the next, to the next. But then you get misalignment and ghosting artifacts. I'll just go back for this video. So the next keyframe, it would still use the warping, so the disparity-based motion fields, but you can see the bench also flickering, or there's this popping artifacts as the keyframe is switched. And with the alpha blending, you can avoid the popping, but you do get these ghosting artifacts when the two images are not very well aligned when you interpolate them. And here's a comparison of all three together. You can see we have the smoothest views, and the frame rate is also very high compared to computing these flows on the fly. So if you compute the flows really on the fly, on the GPU, then we get about 1 frame per second, which is not a very good experience at all. But when we pre-compute the views, the flows, and do flow arithmetic, then we can achieve 40 frames per second, which is close to what we really want to have ideally. So we can also compare sort of these different these different blending techniques by looking at consecutive images and sort of creating a worst possible case where from one frame we go to the next frame and this changes the keyframe. And when we do the next keyframe-based method, you can see that there's quite a noticeable difference between these two images when you compare them and you compute the difference map. So these are the popping artifacts when edges of objects suddenly pop to the side, for example. With the alpha-based blending, you can hide these a little bit, but you get ghosting artifacts around the edges. You can see this perhaps a little bit up here on the top of the bench. The top is not aligned, so you get these ghosting artifacts. And with the flow-based blending, you can get everything nicely aligned and the difference images. It's very, very small. So the results are quite good, but we do need to capture quite a lot of images. So this does take about 2 hours. For outdoor scenes, it's a little tricky, as I said, because shadows move, clouds move. So this is not very practical in an outdoor setting. You can use it in a lab, for example, where you need to look at ways of making it faster to capture. Also, if you want to extend it to videos, you then need to think about how you can capture everything quickly enough to also accommodate video input. So the flow could be improved a little bit, as always, but what we had worked reasonably well for us. And it's quite a bit of data that you also need to capture then, of course. So we have these 576 frames, and we have disparity motion fields for each and pairwise flow fields between, quite a lot of pairs in between. So still quite a lot of data that still could be compressed more efficiently, but we didn't look into that very much. And also with the approach that we've taken, there's no guarantee that all these flows are actually consistent. They're just using always very local information, so you can assume it's sort of locally smooth. But as you go between pairs or triplets of these keyframes, sometimes there are some inconsistencies. And in particular, if you have periodic texture, then optical flow might not be the best way to align things, because it might align different parts of a fence, for example, differently. Not in the way that that's geometrically correct, just that it would visually match. And so that's the limitation of our approach still, because we only use optical flow and no actual geometry to constrain the flow or the motion between frames. And I mentioned that Google has also recently released something similar. So they have built this camera rig with 16 GoPros that captures a spherical light field. And that's a little faster than 2 hours. So that's good. That's good progress, definitely. But they don't have quite the same capture density that we have. So essentially, they do have sort of like almost the main 5-degree steps that we have, roughly. But they don't have these additional frames that we use for computing the disparity flow fields. So I would argue that our representation is a bit more accurate, but also this is completely light field based. So it's completely image based. As far as I know, they don't reconstruct any geometry as well. So it's completely image based. But it's already a good step forward, because this makes it much faster, much easier to deploy. And you don't need 2 hours in the space shuttle. You just need I don't know, half an hour probably, setting up everything and testing it. So that's all good. So what we've shown is a complete system that can capture a 360-degree environment and give you stereo vision, but also head motion parallax. So that's also for the first time enabling you to look around things a little bit, to move your head a little bit and have the scene react to that. And for that, we created a new image-based representation that's based on these 2-layer flow encoding. So we have the disparity flows and pairwise flows between images, and we combine them to robustly interpolate new views with flow-based blending to reduce artifacts for popping between pairs of images, but also to align things smoothly and give you a nice visual result. Yes?
What's the sort of practical limit for the extrapolation here in terms of parallax?
I assume you could not go much further than from one keyframe to another. So I assume the sampling density of the keyframes is what is sort of required. You probably can't go much further than, I think it was 5 centimeters with that. So we do need to have a certain density of these keyframes so that we can interpolate between keyframes and then jump to the next one as required. Are there any other questions perhaps on this?
So how important it is for user experience to have parallax? As a person without stereo vision, I think it's great that you can but if you put someone in that's not familiar with it, would they see a difference between stereo and stereo plus parallax?
I think they would subconsciously notice that there is a difference when they start moving the head. If they're always rigid with the head, then they wouldn't notice that. But I think it just gives you a really nice feedback that you also know from the real life. And if you're sort of expecting head motion parallax and you don't get it, then you sort of get contradicting cues. And I think it's one aspect that contributes to discomfort in virtual reality with 360 videos, for example. But yeah, head motion parallax is super important if you don't have stereo vision, because then you can get a good idea of the depth structure of the scene. Yeah?
For those 4,000 pictures, you're capturing with mechanical methods. You either move the camera or put it on a sphere. Have you think about using optical imaging techniques, like any fast scanning methods to capture those images without moving the camera but changing your optics?
Optics.
Yeah.
I think we probably do that as well. It should be equivalent, but I'm not very familiar with these with other capture setups. So that's sort of the first thing that comes into my mind when I want different viewpoints. Okay, let's just move the camera around. But yeah, it's not very practical, I agree. And if you can create other optics where maybe the optics sort of scans around, that could be more useful. In particular, if you could design the optics like catadioptric optics where you have a large field of view, then you could capture more at the same time, perhaps. But you still need to change the position at which the image was captured to actually capture some parallax in the scene. So it's not like in a normal panorama where the optical center is always in the middle and you capture everything in all directions, right? You need to move the camera as well, somehow, or at least move the optical center of the camera. Maybe the sensor can stay in the same place, but you move the lenses around and add some mirrors in there, for example. I don't know. but I think it would be possible. Yeah.
So you have a budget of 3,000 images or so, and you use them to take 500 image samples plus use these 6 for finite difference gradients, essentially. You know, sort of as I move in this direction, you know, how does the image change? So is this optimal, or can you take your 3,000 image budget, spread them more evenly over the sphere, and fit images plus gradients everywhere?
I think that's a very good question. What we try to find is a trade-off between what is captured and what is stored in the end. Because ideally, I want to capture everything and store everything so I can access it at runtime. But it's not very practical to load 4,000 images into the GPU and just have them all there, or stream them in and out on the fly all the time. So I think we try to find a trade-off there where we can compress the representation a little bit so that we have these main keyframes and sort of the motion encoded relative to these keyframes. And one thing I glossed over was also that these motion fields are actually computed on patches of 8 by 8 pixels, so they're not per pixel flows as well. So they're much coarser, much more space efficient as well. So, but I think there's probably still space to explore other trade-offs in that area. I think also, particularly when you get closer to the poles, having a 5-degree step is not going to be very useful, because then the step length is actually quite small up there. So then maybe a regular triangulation of the sphere would actually be more useful, perhaps. But this is a little easier to code, I guess, and run. But yes, I think it can be optimized further. Okay, so then I would like to move on to one of our upcoming papers at CVPR, which we titled LIME, Live Intrinsic Material Estimation. So this is with collaborators at Max Planck Institute for Informatics and also Matthias Zollhofer at Stanford. And what we want to do here is invert the rendering process, essentially. So you might be aware that in rendering you can formulate everything theoretically using the rendering equation, where you have as inputs some geometry, you have some material or some reflectance, and then some illumination. And you can combine all of these to create a rendering, create an image of a virtual object. An inverse rendering, then it's just inverting these two. So we want to go from a single image, ideally, and reconstruct the geometry, the material, and also the illumination. Now, clearly, this is very ill-defined. It's a very complex problem. So people have tried different approaches for just reconstructing individual aspects of the input. So for example, for capturing the materials, people have built Gonio reflectometers with different light positions, different camera positions to capture the properties of a material, the bidirectional reflectance distribution function, BRDF in particular. Now all of this again takes quite a lot of time, because you need to sample all the different combinations of a material, positions of light and camera relative to an object. But what we would like to do is sort of do an inverse rendering in just a single image, get as much as we can from a single image, and not take several hours of capturing lots of data and reconstructing it very accurately, by doing a very quick, sort of quick and dirty way of reconstructing things. So what our problem then was that we wanted to solve is to reconstruct the material. We don't want to reconstruct the geometry or the lighting necessarily. You'll see later on that the lighting actually falls out if you have some extra information. But the geometry, we don't reconstruct that. That's quite challenging from a single image. What we want to do is attack a different angle that hasn't seen much work, too much work. That is to reconstruct the material only, regardless of the geometry and the lighting. So what has been done before, there's some deep learning-based methods that train on lots of synthetic data, for example. So you render lots of virtual rocks in front of some background and let it reconstruct some texture, environment map, and then you can compare that to the input, and you can get reasonably close if the data you're testing on is quite similar to the training data, but this doesn't really generalize very well. And then in rendering, you can also see that actually rendering things with physically accurate models is also can be very expensive. You need ray tracing and lots of samples per pixel to create a high quality rendering of what a material might look like. So sort of synthesizing an image that you would expect from a material model might take you half a second. So then this is also not very fast to sort of iterate and optimize this. If you change the model parameters, your material, you want to render that again to compare to the input image, then if every optimization step will take you half a second, it'll take you quite a while to actually converge to the material. And there've been also some papers that use variational methods for optimizing materials and normals at the same time. But the rendering equation actually conflates all of these things together, so there are a lot of ambiguities, so you need to build in strong priors if you want to reconstruct all of these things at the same time. So it's very under-constrained, really. All we have is a per pixel color. We don't have any idea of the geometry or the lighting or the material, so there's quite a lot of parameters in there. It's also a dense problem, so for every pixel, there's a potentially different normal, potentially different lighting, but we assume that, for example, the material is consistent. So we can try to estimate the material from all these different samples that we have across the pixel grid. And yeah, it's quite a high-dimensional problem because the geometry can be arbitrarily complex, the lighting can be fairly complex as well. You can represent it as an environment map, for example, and then you get a lot of pixels that can change, the lighting that can change, and then create a different rendering or different impression of the image. But we can use some natural subspace priors. So we can sort of approximate the material using a simple reflectance model instead of, for example, using a completely data-driven BRDF model, which can have hundreds of parameters as well. We can use other models that are sort of representing particular classes of materials with just a few parameters. So this has been used in deep learning-based methods, for example, that estimate both the illumination and also the material from an image, for example, for image of cars. So this is trained on rendered car images where you have ground truth label data that you can train on, and then you can test it on new cars that hopefully are close enough to your rendering data. And some other techniques also try to reconstruct the illumination, surface normals and material, all of that together. But here they're really relying on a very strong prior that what is going to come in looks like a car. And if we trained it on thousands of cars, then this works reasonably well if you pass in a new car. If you pass in something else, that doesn't really work. So it's only specific classes of objects like cars or chairs, whatever has been trained on these networks, these work then, but they are severely overfitting. So if you pass in something new, like a coffee cup, it expects a car, so it'll give you something, its best guess, but it's probably not any good. So what we try to do, as I said, is to reconstruct the material from a single image. So we have an image of one object with a constant material, and we have some background. We don't know what that is, just something distracting that we don't care about. So we need to segment the object out of there and then estimate the material, regardless of the geometry and also regardless of the lighting. So what we need to do first is segment out the object so that we can concentrate on that and ignore the background. But we want all of this to be as fast as possible. So we can do it in real time. We can reconstruct materials and insert objects of materials that we captured into a video with augmented reality live. So you don't have to wait until the materials are reconstructed or estimated to insert new objects into an existing live scene. And also we would like this to be more general, not just working on cars or chairs. We want to be able to support any shape, essentially. So how do we do this? How do we make this task easier for CNNs, but also prevent this overfitting that previous techniques had, that overfit to a particular class of objects like cars? We want to make it as general as possible. So what we're using here is a sort of an approach based on image translation instead of regression. So we're not learning directly the model parameters from the input, because that is quite a complex transformation, actually. What we're doing is we are decomposing the problem into several steps, use image translation steps between them, because these are very well constrained, and we can also generate lots of useful training data for that, and then make use of the actual rendering process to constrain the learning process as well. So what we're doing as sort of our subspace of materials that we are supporting is essentially Blin-Phong rendering. So it's a very simple rendering model where we have diffuse appearance, we have specular appearance, and we can reconstruct a large range of materials with just a few parameters, 5 parameters, I believe. So we want to decompose our input image I into a diffuse albedo, a diffuse shading, and then a specular albedo and specular shading. And we can actually create all of this for our training data easily. We can pick a large range of objects, such as this chicken, for example, different objects to make it more general, to not overfit on cars, for example. Use a random input image from Flickr on the background, and then we can constrain it that it's very dark here, that the diffuse shading is a combination, it's combined with a diffuse albedo, so the main color of the object, the diffuse color of the object, and then this is combined with a specular color as well. So the specular shading, the highlight. And in our model, we assume that the highlight, oh yes, that's a bit better. So you can see it very faintly here, the diffuse shading, and the specular shading is just the white highlights. So in our model, we assume that the highlights are white, which is often the case with sort of plastic-like materials. And this then gives us just a few parameters that can represent a large range of materials. Okay. Looks like the battery has died. So the way we are reconstructing or building our approach then is we use an input image from a webcam. We feed this first into the segmentation network. Right? I mentioned we need to isolate the object first so we can focus on that and discard the background. And this is an image-to-image translation task, so we use a standard UNet architecture for that. And then based on that, we can multiply the mask with the input image, and then this extracts just the object we're interested in. And this masked object, we then decompose first into diffuse and specular components. And we don't reconstruct both at the same time, because we know that if we add them together, they should give us the input. So what we're reconstructing first is the specular part, the specular component, so just the highlight. And then to make it right, and for the albedo part, this can then be learned from a combination of these two, right? From the segmented image and the specular component of the image, we can then learn the albedo part. And one step we added that we found very useful is to make the specular image into a sort of a mirror-like image. Because for the specular image, this will depend, it'll look blurry a little bit, which depends on the shininess of the object material. So some materials are very shiny, they're very sharp and crisp highlights. Others are more dull, and so they have more diffuse highlights. And so what we do in this mirror net is we actually learn a transformation to an image as sort of a specular version of that material with a very shiny material. So how would it look like if it was a mirror, essentially? So you can see the highlights are more sharp, and this sort of, it normalizes out the shininess component of the material model. And then we can use both of these, the specular part and the mirror-like part, for determining how shiny is that object actually. So what is the specular exponent that we get, that we need for our material? So is it a very shiny object, or is it more dull? How dull is it exactly? So this is reconstructing that component individually. So you see we are decomposing the whole problem into several individual steps. Each of these steps are more well-defined and simpler to learn and train, and we can generate training data actually for all of these intermediate stages. So we can train all of these networks individually, and then we can train everything end-to-end, fine-tune it, and make it work end-to-end. And the output of everything is our material. So it's 5 different parameters. It's a diffuse albedo, 3 components RGB, the specular albedo, one component, and the shininess, which is another component. And what we do is we train this completely synthetically. So here you see all these intermediate stages visualized. So we use different objects to make it more general. We have ground truth masks, obviously. We have the diffuse shading, the specular shading, and this mirror-like version. And we also in our data use different environment maps that we captured, like for indoor environment maps, so we have some variation there as well, that we can apply it indoors easily, that is more robust to different lighting environments. So we do some additional data augmentation on that. We rotate them, for example, just to make it more complex, the training data. Even though it's all completely synthetic, but we want to make it sort of as general and as flexible as possible. And then when we apply it to real-world objects, you can see that it actually generalizes very well. These are 5 different objects. They're not all plastic, right? But the segmentation works pretty well. And then we can reconstruct the material parameters and visualize the material on these reflectance spheres. And you can see that they really well approximate the main material, the look of the materials. Here are a few more of these. And you can see, for example, that the diffuse layers, it does remove the specular parts as much as it can for these like 2 reflection lines on the cup there, and then reconstructs this mirror-like version that look similarly shiny, regardless of the actual shininess of the material. But we found that this is important to separate out all of these steps because they're all confounded together in the rendering equation. So quantitatively, we found our approach to work pretty well. It is not best in all individual categories when we evaluate the albedo for the diffuse and specular and the shininess, but we found that overall across all the categories, we have the best trade-off. So our full approach does very well on the specular albedo, for example, and you see that other approaches do really well on diffuse albedo, like the bottommost approach, reflectance maps, do really well there. But for the shininess, it is actually very bad. So it usually goes, expects things, or predicts things to be much more shiny than they actually are. And what we did for the shininess is we sort of reconstructed 8 different bins, so different classes of shininess. And you can see that in the confusion matrix, it's actually very close to the correct detection, that it detects the right shininess for each input material. Here are a few comparisons. I'll skip to to this one, for example. So this to-do list paper was just for cars, for example. We can apply our technique also on cars. There were no cars in our training data. It was just other objects, but we can see that we're still doing reasonably well at reconstructing the material of the car just from a single image. And what we can do with that is we can clone existing materials. So from the single image, we optionally can also use normals. So if you have a depth sensor, you can capture that, and we can use the normals then to reconstruct a simple reflectance map, a simple lighting representation for relighting the objects, because that is still the unknown. In our main approach, we don't reconstruct any illumination, no lighting. And if you have no lighting, it's difficult to insert the object that it fits in nicely with existing scenes. So you do need to have some idea of what the lighting is so you can insert new objects. These are some intermediate results, and this is what it sort of looks like live. So we're cloning the material of this water bottle onto the bunny, and at the same time we're reconstructing a basic environment map at the top left, and then we can visualize what the estimated material looks like under that environment map. So what would a sphere of that material look like in this environment? Here we have another more shiny material from this red car, and we can clone it onto the bunny as well. And you can see that the highlights seem to come from the right directions where you would expect it to come from. Apologize for the very jerky camera. So here's one more, copying the material from the little rubber duck onto our bunny. And you can see over time it builds up this lighting environment representation. So the environment lighting is quite coarse. It's not very accurate, but this is mostly to do with the material. The more diffuse material is, the more low-pass filtered your environment map is when you reconstruct it. You can't reconstruct very high-frequency details in the lighting because the material always looks very matte and diffuse. So it's physically impossible to actually reconstruct very high-frequency reconstructions from that. So the best we can do is use something like that. So what we like to look at in future is other models of materials. So what we used, Blin-Fong material is very sort of basic and simple, and a model that is only applies to a class of objects. But with more non-parametric BRDF models, we could use, for example, a large database and reduce it with PCA, so we can actually reconstruct much larger and maybe more realistic range of materials. I'm also interested in looking at spatially varying BRDF, because there's only so many objects in the world that have a constant single material, and we want to be able to reconstruct more complex scenes with several materials. And something else we find really interesting is sort of multi-view, because if you have multiple images or multiple perspectives on an object, then it can tell you actually quite a lot about the materials. Because in one image you might be missing specular reflection highlight that you can capture in another view. And so having more views gives you more information about the material, about the BRDF. So we want to combine all of this information together to reconstruct materials more accurately. Any questions? All right, well, in the interest of time, I will then skip ahead a little bit. To our upcoming SIGGRAPH paper called Deep Video Portraits. This is a collaboration with a few different groups, mostly at Max Planck, but also Technicolor and Technical University of Munich and Stanford University. So what we are trying to do is to resynthesize a phase from a source sequence and a training sequence or target sequence. So we want to transfer the expressions and pose from one video into the video of another person. So for example, here we make Obama move his head according to our source sequence. And how do we do this? We do it by reconstructing the motion and poses of the two input video sequences, and then learning a mapping that combines the new motion information with the existing training, with the existing target sequence. So we do, like I said, we have two input videos. We have a source sequence and a target sequence. And we apply monocular phase reconstruction to both of these. And this gives us a phase model that captures the expressions, the pose of the phase, the appearance of the phase, the identity, and also the eyes. So it sort of encodes the most important information about the phase. It doesn't encode a very highly detailed texture model, for example. But it does tell us everything sort of about the lighting and the expressions and the pose of the head. And we do this for both of the sequences. And then when we have these parameter vectors, we can recombine them in a new way. So I will show some applications that combine just the expressions, where we only transfer the expressions from one video to another, but we can also transfer the pose, for example. So here what we're doing is we're taking the pose, so the head orientation and the translation, the expressions and also the eyes, so if you're blinking or where you're looking, we transfer that, but we want to keep the illumination and identity the same as the original target actor. Then we render some synthetic, just computer graphics renderings of this face. So we use just a standard diffuse look of the face, so just a shaded colors. We also have a sort of correspondence or UV map style rendering, so that our next component knows the spatial relationships of parts of the face. And then we also have another layer of where the eyes are and where they're blinking. And all of this we pass into a new rendering to video translation network. So we're passing in renderings. What we're getting out is a real looking image in a way. So this is, again, it's the sort of image translation task, right? We pass in lots of synthetic data, which you can drive with whatever animation data that we want to use. In our case, we use it mostly from the source video, but we can also use completely different inputs. And then we synthesize a video one frame at a time. So this is what it looks like, these intermediate layers for our synthesis. So we have this shaded rendering, and this is sort of the best representation of Obama in our model. The model is not very good. It's mostly was created from Caucasian faces, so it's not a very good approximation to Obama. But we do nonetheless use it, and it works really well for us. We have this correspondence image, and we have an eye image. And you can see there's blue pupils in there, and when these disappear, then it's blinking. So we can also encode that, because that model can blink, for example, but it can't actually look in different directions. It's not encoded in this face model. Here's another example where you transfer the pose and also the expressions in the eye gaze. And you can see, for example, that with our learning-based approach, it also synthesizes the shadow of the person behind it correctly based on the motion of the head. What we're doing here is only transferring the expressions. So we're keeping the head pose the same. The head pose is the same as in the target sequence, but we're only transferring the expressions of, like the mouth expressions and the eyes, onto the target actor. And you can do that very selectively. So here we have a sequence of Theresa May where we just fix the pose, for example, so the head is not moving. We keep the mouth fixed as well. She's only blinking. It's very creepy. Here we keep the expressions fixed and only copy the pose over. So that's just an illustration that we can do this selectively as well. And there are useful applications. I will show those as well. So one particular useful thing, or sort of really interesting thing, is this interactive editing. We can modify all the parameters of our face model interactively, pass it through our network, and then create a realistic-looking image. So we can change each part of the mouth, for example. We can close eyes, raise eyebrows, all of this individually, and create a synthetic, a realistic-looking synthetic image out of this. Here's another example that sort of visualizes the range that we get. And our network's only really conditioned on the face model, so we don't have any idea what the background is, which is why we assume it's a sort of a static background, because then the network can learn that quite well. But you might have noticed also that, for example, the t-shirt, it also changes relative to the head. So the pose of the head changes, then the pose of the upper body also sort of implicitly changes as well. So this is nothing that's explicitly encoded, it's all learned, essentially. And we also change, we try experimenting with changing some parts of the identity of the face. So we can make the face a bit wider, for example, and you can see that the network also extrapolates a little bit for that.
Is that final network that does the rendering a sort of generic one, or is it trained per individual?
It's a specific one that's trained on a specific target sequence. So it's not a general approach at the moment, but it's trained on just a few thousand frames, so just a few minutes of target footage. I have some other comparisons to that. So here we're comparing the face-to-face approach, which is sort of an optimization-based approach for transferring expressions, but it doesn't transfer head poses, for example. So you can see that in this approach, the head is always in the fixed pose, in the original input pose. It can't change that. It can't change the pose in addition to the expressions. This is an approach from SIGGRAPH last year. This was trained on 17 hours of video footage of Obama, and then it can create realistic-looking videos of Obama just based on audio. So essentially, just it's audio to Obama. So it's learning the mapping from just the audio track to the video. But this requires 17 hours of video footage, which is not easily available for most people. And in our approach, you just need like 5 minutes of video footage to train on. And one particularly useful, oh sorry, I skipped over that. I think one particularly useful application of our approach is for dubbing, because we can change sort of the mouth expressions to really be well aligned to the voiceover track. So if you have a, for example, German movie and you want to bring it into a British cinema, then you could dub it with English, but often then that desynchronizes the mouth movement and the audio track, and we can synthesize, resynthesize the face, essentially, the whole face, or just the mouth region, based on the audio track. So then it's really well aligned. And we're comparing to a different technique from Eurographics 2015. Actually, these two, the labels are swapped. Sorry about that. You can see that in the previous technique, it was sort of looking, the mouth region was looking a bit more rubbery, whereas for ours it looks very natural, and it's very synchronized to the input. Here's one more comparison to a paper from SIGGRAPH Asia last year. It's not a fair comparison, really, because what they use is they use a single image and then drive it based on a video sequence, whereas we have two video sequences as input. So you can see that in the background, for example, all they can do is they can warp the background. But the face changes are actually quite realistic as well. But for us, we synthesize both the face and the background and everything coherently. But that's also because we have more training data. So here's a comparison using self-re-enactment. So we use a longer sequence. We train our network on the first half, and then we try to recreate the second half based on the tracking of that. The reference is what it looks like in real, as a real video, and this is our reenactment result, self-reenactment result. And you can see that there's very small errors in between them. So for most of our results, we have resolutions of 256 squared. These results are 512 squared. This takes about 40 hours to train, and we also tried a 1024 squared result, and that took 3 weeks to train. So it's very expensive still, this. And it's user-specific, and not even user-specific, it's video-specific. So it's a very interesting question how to make it work more generally, or how to adapt existing networks to new speeches, for example, or new video recordings. In our network, we also have built in temporal coherence. So the input to our network is actually 11 frames, like a history of all these renderings, and then we predict one frame based on that. And you can see that it improves the temporal consistency quite a lot compared to a single frame approach, where you would only give in the face model for one frame, one time frame, and then predict one video frame from that. So we definitely improve on that. And then we also compared the quality of the reconstruction results of the videos depending on the size of the training data. So if you only have 500 frames, then it can be quite coarse. Some of the poses that you want to create in the video may not be in your training data or even close in there. So the more data you have, the better it gets generally. So most of our results are about 2,000 frames, which is just 4 or 5 minutes of video footage. And you can break it quite easily still. If you move too far, if that's not in the training data, then the network doesn't really know what to do. Some of the expressions are also really very challenging. Politicians may not open their mouth very much, but if you then drive a video with a very large mouth opening, then we don't really know what we can do there. We don't have any particular explicit model there, or what the mouth interior looks like, for example, right? Or if, in this case here, it's just too much motion, then the background is unknown behind the person, for example. And with that, I would like to close. Thank you for your attention.
Thank you very much, Christian. I think we have time for a couple of questions.
So this was
Yep.
human to human. Have you tried human to a robot or animal, or could the same be?
I think we wanted to try human to cartoon, something like that, but the time was running out before the deadline a little bit. So I think we tried that. The problem with that particular data was that the hard color edges in cartoon videos weren't really well encoded in this network architecture, so everything came out really blurry. But I think with a robot, it might work. I mean, what we need is a way for sort of tracking the robot, the motion tracking as well. So that probably wouldn't work very well with our face tracking. Like there was also, for the cartoon videos, the tracking failed for that. So then we don't have the right input data for our pipeline. But if you provide that data or get it from a different approach, then we could try that, yeah.
Did you
thinking about larger head motions, I presume it doesn't work to segment the head from the background. It doesn't make any difference to the performance.
We tried it on some larger head movements as well, but at some point then the monocular tracker also stops working and braking. I think 45 degrees is sort of when it usually stopped working. Yeah. So then that's the main limitation there. But I believe if we could track that, then we could, then it should work.
But did you have trouble synthesizing? You know, would it be better to use something a bit more sort of engineered to try and get the hidden background synthesized, or do you think the network could just do it?
I think if it has never seen the background, it doesn't know what to do. That's sort of my interpretation. I think it would be a really interesting approach, and that's actually something we're looking into in the moment as well, how we can separate foreground and background and then recompose it later. Because once you can separate foreground and background, head and background, then you can in-paint the background as well. Exactly. And if you have a specific task with that, then you can also expect a better quality result out of it in the end. All right, thank you.